Well, you can read clearly radical bromination, okay? What's NBS? And bromosuccinimide is a source of what? Bromine radicals. AIBN. AIBN is a radical initiator. It wasn't covered on the handout. It's a very unique one. You're probably not going to find it in a textbook. Instead of an OO bond, it's got an NN bond. And it will generate radicals. It's a radical initiator like peroxides. They're using carbon tetrachloride again, yeah? Reflex 2 hours. They're getting this product. Huh, what's going on? Telling you it's a radical bromination. If you just look at the reaction, it's an addition reaction. No, actually it's not. If you look at the formula, the difference in formula is that's got an H where now this has a Br in place of an H. Look at the formula. It's really not an addition, it's a substitution. Okay, do mechanism for that reaction. Do it on that cover page if there's room. Just mechanism for that reaction. You don't worry about the AIBN, etc. Just start with bromine radicals. Bromine radicals are generated. Also, don't really worry about propagation so much because we really don't. If we were starting with BR2, we might be able to show propagation. So it just shows sort of like, 75% of the mechanism. What's going on? Has nothing to do with this over here. Okay, we talked about alkanes. Well, the substrate doesn't have to be purely just a hydrocarbon alkane. Any questions about the mechanism? Anybody would like to ask a question to get you going? That's the question. The mechanism should show the double bond movement, right? Okay, bromine radicals, right? I told you to start with bromine radical. Where are you going to extract an H to make a radical at on the substrate? Well, the first step is extracting an H from your substrate, right? That's what the mechanism. Well, if you want to extract an H, maybe we need to see which H has been removed. Has one been one? What H has been removed when we go to it? If you look at it, there's two H's there, but there's only one H here. How many H's there?
One.
How many H's on each carbon of the alkene?
One.
One. How many H's on each of these carbons?
Two.
There's one there, and there's one there. Those H's are still there. So which H has been removed? We identified it. So have the Br radical remove it, abstract it. And when it abstracts it, you form what? HBr. Yes. Okay, I'm going to abstract an H. I'm going to say this electron is going to team up with one of those. The other electron is going to stay behind on carbon. That's going to give I'm not going to try to draw that over there, okay? It's not, nothing changes over there. Let's just focus on up here. Now we have a 1H there, and now there's a radical there, right? Plus HBr. Okay. Now what do we want to do? Is this going to capture a bromine radical? Again, if we just capture a bromine radical, we may be a termination, and we're not using bromine, but ultimately, in any of these reactions, it captures a bromine. Do we just want to bond a bromine here? It would be that product. We got to get it over here. What do you think we might want to do here? Joe?
We could move the pi bond.
By what?
Take one electron.
By what process? Resonance, yeah. Did we do resonance or radicals yesterday?
You did.
Yeah. There's resonance. We can move one electron here, this electron here, and what are we making between these two carbons? Another bond, and it will be a pi bond. This other electron, let's move here. This is just resonance of the radical. Double bond where we need. Now we have radical down here. I'm not going to draw in the H's anymore. We have all that stuff that's somehow there. It's just resonance of the radical. Now what do you want to do here? This reaction may actually not be propagated. I'd have to look at it. It's not the same propagation discussion as we did with BR2. I'd have to look at what's going on. You got NBS. Because when we extract the bromine from here, we're not going to make another bromine radical. That's NBS. That's supposed to be a five-membered ring. This can here, and this can go here. We're making the carbon-bromine bond. That gives us final product, right? Yeah. Unfortunately, we don't create a bromine radical over here. We actually create a nitrogen radical. And that's the problem that I'd have to think about. How do we propagate and create other bromine radicals? I don't want to really think about it because we're not doing this standard mechanism. Okay. We also have an odd generator. In the end, we know that we can quench. The main thing here is seeing up to this point and recognizing the resonance. And they make this a 95% yield, which tells you it's highly selective for this to capture a bromine radical as opposed to that. Capturing. Why? That would be some advanced considerations. For some reason it was. They make that compound. Question, does it make sense? Just got some resonance of the radical in there. And we did not react with the pi bond per se, it just sort of was there for resonance. After they put the bromine on, what do? Actually did a reaction we know, I just didn't label it. What are they doing when they go from 65 to 66? Well, it also kind of involves, it's a little bit, it's an elimination. Putting in a double bond, but it's called a vinylogous elimination. Put your pencils down. There's an H here. the base, whatever the base is, takes the H. These electrons move here, these electrons move there, and they get kicked off. So it's like an E2 with a pi bond, with some pi bond in between. That's legal, but we've never done anything like that.
Okay.
Would that electron movement give 66? That's the more important thing. Does that electron movement give 66? Yeah, base takes the 8, electrons move here to make pi bond. This moves down, make pi bond, and gets kicked off. That's an E2 with some resonance in there. Okay, maybe that's why I didn't label it, because it's a little bit odd. So they put the bromine on, then they took it back off. And when they took it back off, they took the H with it, and you can eliminate. Like we said, you often put these halogens on, so then you can do chemistry and do maybe substitution elimination of halogen. A Bach group, that's an abbreviation. The Bach group is shown below, I think. It's got a carbonyl. It's really an ester. Or somewhat. Ultimately, as I said up here, we didn't refer to it, but the very first step is actually what? 4 plus 2? 6-member ring is this turned. That is a Diels-Alder. But look at this. They're showing it as a chiral product, not racemic. First off, final exam review. Is that RS?
Yes.
Yes.
Carbon dioxide is going to be 1. Same. Not same. We hit this here, and there's going to be 2 bonds to carbon. This only has 1, so this is going to be 2, 3. H is 4. R. H is 4. So what is this?
Yes.
It look like it's S? How do they get only S? Now that'd be optically active because it's chiral and it's only one enantiomer. By the way, they're saying they get greater than 97% EE. What's an EE?
Enantiomeric excess.
Okay. And that's, yes. Can we say this? So what's the ratio of this? That this means that it's 97% EE of S versus it implied that the other one is R. So they didn't get 100% S. I got a little bit R, but if you turn this into a ratio, do that. What's the ratio of S to R that they got?
1.5 to 98.5.
98.5 S, 1.5 R. If that cancels 1.5 with this, what are you left with? 97 EE. Yeah. They got 1.5% of R. That's not too bad, though, in terms of enantioselective. It is enantioselective because it's not 50-50. They didn't get 100% enantioselectivity. But this is going to be optically active because it's not racemic. It will have some optical activity. But this is not optically active. Well, this is an example where they're including, this is actually an optically active catalyst. And there's a million of these. But this is what imparted the chirality or the optical activity in the product. Because if that wasn't there, this would be racemic. 30-hour reaction. But that is a Diels-Alder. So there is some chemistry there. Okay. So that was an example of what we did on this first page. Had some resonance. And ultimately, even though that pi bond was there in that substrate, we were still doing an alkyl, or sort of like this. I mean, here we did radical. But didn't we also show how you can do a resonance and end up with the bromine over here? That's like the one on that handout. Let's do the, let's look at the other page. Okay, there's another type of radical reaction involving bromine. But this is not bromine, L-little bromine. This is just involves a bromine atom. Actually involves HBr. This is the one we skipped when we did alkene reactions. Let's look at it. First, some review. If we have an alkene, we can make this product here, which is we're adding water to the alkene. We're hydrating the alkene. That can be done with aqueous acid. Attack H+, make cation here. Water attacks cation. And then you lose an H from oxygen to give that product. You can also get the same product by doing this two-step process known as what? Oxymercuration, followed by reduction. Okay, you should know that mechanism. He gets the same exact product here. You're not going to get any rearrangement. If rearrangement was possible, this would probably rearrange, but this would not, right? Because this involves a mercuronium ion that will not rearrange. If you want a DOH on the outside carbon, you can do it this method, hydroboration oxidation. That would give you, we call this Markovnikov, or the sort of standard chemistry. This would be called sort of non-standard, because you say, hey, I make cation here. Ultimately, we got oxygen. Somehow the parent nucleophile ends up out here. Call it anti-Markovnikov. Okay, we get that product. Over here, HBr, we would expect this product here. Standard Markovnikov addition of HBr to an alkene. Well, how do we get the Br on the other carbon? Which we would call an anti-Markovnikov addition of HBr. We never did that. It can be done. It's HBr plus what? Peroxides. That will give anti-Markovnikov. And this is what's on the puzzle. There's one of these. And because there's peroxides there, that's a big clue that this is actually a radical reaction. Where this up here is a good old-fashioned ionic reaction. Everything up here is ions. H+. Alkene attacks the H+ ion. Before we'll make carbocation. Then the bromide ion attacks the carbocation. Everything's ions. This is going to be all radicals. But we're using HBr, not bromine. Now, when we get through, we're going to have to say, don't confuse these reactions. Okay? Bromine radical is an alkyl reaction. HBr radical is a alkene reaction. After we do it, you may look and say, why doesn't it do alkyl radical? And I'll say, I don't know. It seems like it should. But this is what you got to know. HBr peroxide is an alkene reaction. We're doing alkene chemistry here. Okay, let's look at the mechanism. Ultimately, instead of H+ being the initial nuclear electrophile, Br radical is the initial electrophile. How do we get Br radicals? HBr. Now, there's different mechanisms you can show to get Br radicals from here. How do I want to show it? I think it's okay to show this heterolytic bond cleavage. Okay. Although this may not exactly be right, I think this is where I'm going to tell it to you. Heterolytic bond cleavage. What is that going to give? One electron this way, one electron this way. That's going to give H radical plus Br radical.
Isn't that homolytic?
yes, sorry. Homolytic, yes. We need to make sure we know what heterohomolytic means.
If we're doing that as a reagent or something, do we need to put it in the presence of light, or what do we do?
See, it's just peroxide. It's actually not explicitly that it's light. You got to get BR radicals. The only thing I'm wondering is, do we want to first show it like this? We could just say it's ionized, and then we could say something takes an electron from that and go from here to here, it loses an electron. Well, this is a different process to get to BR radicals, and I'm just wondering, I'm not sure. But we also are going to have H radicals at some point. So while to me this may be a little bit more intuitive, because I don't think it's what you're going to see in the textbook. Let's just do homolytic bond cleavage, get to here. But ultimately this reaction begins with bromine radicals. And ultimately we say that peroxide, the presence of peroxide causes this to form bromine radicals. Now this reaction is a little bit not great, because if you don't get bromine radicals forming fast, the alkene might just react with this in the regular style. So you got to hope that it forms bromine radicals pretty fast, and you don't have any just ionic HBr, or because you might just get the regular Markovnikov. But here's the mechanism for getting the anti-Markovnikov. Get bromine radicals. Then here's where we're going to do something different. Pi bond's going to react with the bromine radicals. Now, same thing. Whenever this reacts with the bromine radicals, we're going to leave a radical here. You'll see. Would we rather leave a radical on the left or right? On the left. The radical is just like a cation. Electron poor, you're going to leave them the same place as you leave carbocations. Radical here. I'm going to redraw this bromine radical over here so I can move my arrows very explicitly. I'm going to move one electron here, one electron here. Team these up, making a carbon-bromine bond. The other electron move here. We got to get the bromine out there anyway. That gives boom, 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 boom. We get a tertiary radical where we would expect it. See, the difference is the alkene is not attacking H plus to give a carbocation here. It's attacking a Br radical to give a radical here. So that's how you get to Br over there. Now, what does this have to get there? Yeah, that H radical just teams up with this, and we get that. Now, what I'm not going to get into is propagation. This is propagated. I'm not sure. All I'm showing you is key points. Bromine radicals. The alkene reacts with bromine radical to leave a radical that's most stabilized. The only way to leave a radical here is for the bromine to bond it out there. When this then captures an H radical, and there's your product, and lo and behold, the bromine is out there, not over here. The peroxides makes it do this. In the end, you can almost just partly memorization. When you add peroxides, what do you get?
Radicals.
You get anti-Markovnikov addition of HBr. Okay, and it is a radical reaction. Okay, let's compare that to previous reaction. What if we took this and reacted it with bromine and H nu? What would that give? Show the product. Anybody got it? Anybody else? I'm thinking bromine's going to end up somewhere in this molecule, at least one bromine. It's going to end up there, there, or there. And there is the same place.
Left.
I'm going to draw a product like that. That make sense? Margaret, why does it not make sense? Maybe I got it wrong.
Well, sort of the way I did it was fairly wrong. I did basically the same first step with the bromine radical.
Okay, you're going to get bromine radicals. Right?
Right,
Okay, you all said bromine radicals this way.
right. So
That's why I told you, we're gonna, at some point, we're gonna say, why did it do that? Okay, so, but this is bromine, okay, so what's this gonna do?
Well, the way I was thinking.
Is it gonna react with pi bond?
No.
Apparently not.
Over here, it reacted with pi bond.
Yeah, this is where you're
What does it do over here?
This is reaction with methyl HCl.
Grabs the hydrogen.
It's gonna strip a hydrogen out. Okay, where are you gonna, and make a radical, where you wanna make a radical at?
Center.
Well, an alkane carbon, you only got two alkanes, we're gonna take an H from here. Electron is going to strip it out, you're gonna leave that leave it behind, and you're going to get boom, boom. That radical, which is actually resonance stabilized. But if you did resonance, it would be, I'm thinking, the same exact structure. If we did resonance, we can move one electron in, one electron here, one electron out. Boom, 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 and get that. But that's the same exact thing. So it's an equal contributor, and if that captured bromine radical, you could still get the same product. But then this captures bromine radical, right? I mean, or from bromine. One electron here, one electron here, one electron here. That gives final product plus Br radical.
I guess my question isn't really about the first part. It's now at this point, looking at your product, why doesn't the pi bond attack the additional Br radicals in your solution?
Because we're doing bromine, we're doing Br218. You see,
You're just
these reactions are bewildering because you're like, well, why come it doesn't do that? Bromine radical. Over here, the pi bond attacked the bromine radical. Right?
Right.
Well, look on the previous page. Well, they're not all. We did this one. Why does this? And here may be answers my own question, but why didn't this attack the bromine radical? This pi bond. We ended up just putting bromine here.
No. You also showed it on the end.
Just the pi bond did resonance.
Right.
Yeah, I mean, you could also do resonance here, but like I said, the resonance would still be the same product because it's identical resonance structure. But we didn't do an addition. On the flip side, we're doing HBr addition, just anti-Markovnikov addition. Okay. We didn't over here, of course, we were using NBS, and we said you could not do it. Actually, couldn't do it with bromine, and that's what I've said here. It would have been good if someone said, hey, isn't the bromine just going to add to the pi bond just so, like you did in the lab and get a dibromide? And I would have had to say maybe, yeah, let's use NBS. But then you say, now we can get bromine radicals, But then you could say, well, why come the bromine radical doesn't have the pi bond? It's like both of these reactions should take place in both cases. But here's the end. Don't confuse it. You got really 4 different reactions. Okay? Now I'll go through the 4 again. Here's number 1. Standard Markovnikov addition of HBr to an alkene. Check. Here's number 2. If you add peroxides, what do you get? Anti-Markovnikov addition to the alkene, HBr. These 2 HBr reactions. Br2 reactions. Br2 with nothing else there, that's just a pi bond reaction, like you did in lab. But what if we have bromine and we somehow make it radical, bromine H nu? What type of reaction is that? Whenever you see that, it's typically not an alkene reaction. It is really a alkyl radical reaction that maybe if you had a pi bond, you'd make the radical next to the pi bond. But yes, at the same time, you'd be wondering, why doesn't this react with the pi bond? Well, maybe it does. But what I'm trying to tell you is in the context of a student taking tests or exams, these are the 4 outcomes. And there are questions about them. You got to get them straight. In terms of predicted product. Now, if you see a mechanism, you have to just be able to work whatever the outcome is. Predicted product, I was going to draw in reagents like I did down here. Does someone want to propose a reaction and we can draw the product? Which one do you want to see here?
All 4.
So,
We can do all 4.
oh, you want to do all 4? How's that?
Let's do the last one.
But you want to do what?
The BRH new,
BR2?
BR2H new, yeah.
Okay, BR2. Okay, you see this reaction here. First you have to assess it. What type of chemistry is going to take place here?
Radical.
Kiara? What type of chemistry? I see an alkene, but I also see just hydrocarbon, alkane carbon. Yeah, I know it's radical because the H nu is going to need a radical, but is it going to react with the alkene or the alkyl? Are we going to strip an H out, or are we going to have the pi bond attack the Br radical? Yeah, see, bromine is typically strip an H, Br2.
So for our purposes, if we see HB, we're going to strip an H.
If you see what?
The HB, the lambda, the light formula at the bottom. We see the H, we're going to strip an H, basically.
I reckon it's the only one of the 4 that had H nu. Because usually HBr, to make HBr be radical, usually it's peroxide. But you could maybe see HBr, H nu. I focus more on the HBr or bromine. Br2, radicals from Br2 are going to strip an H. Okay? Where are you going to strip an H from? It's a complex.
On the bottom.
Which H is, how do you know which H to choose?
One on top.
That's a good question, because if a methyl wasn't there, it'd be easier. Okay, where do you want to make radical of that? That's the question. Would you want to make radical on this primary carbon? You could do resonance and put it there. It'd be primary secondary. Or we could make it here and do resonance be secondary secondary. But then that and that are not the same.
Couldn't you do it from the 1, 2, 3,
I
3
see.
position?
If we do the top,
Yes, it's going to be tertiary.
secondary, tertiary. Yeah, I think I'm going to do the top. We strip an H. We got Br radicals. Take strip an H, leave this behind. It's supposed to be an arrow leaving it behind. And I'm going to get, boom, boom. There's an H there and there's a radical plus HBr. We'll have to look at this. This could then strip the bromine, and we can get a product that looks like this. But there's another possible product that could come from resonance, right? Because we could do resonance here. Where this electron comes here, one of these comes here, the other one comes here. Pi bond here, radical there. I mean, that new H is, that's not a new H,
It's
is it?
old
That's actually old H.
H is on HPR.
Then this could, boom, boom, boom. It's kind of like on the cover sheet of the E2 where that pi bond sort of moved via resonance. Two different products. Can we predict which one might be a major product? I think we can. It's a disubstituted alkene. That's a trisubstituted. I think this may be major. What if we didn't have the H nu? What if it was just bromine? Show that product. How about that? Plus what?
And then our,
Yeah, does that look right? Transition of Br2 across the pi bond.
Yep.
Okay, what if we just did HBr?
It's gonna be racing make only one problem.
I'm not thinking racemic. Give that, right? New H here, Br there.
Yeah.
Where are you going to make cation? Bottom? Bromine text cation? That's not chiral, though.
Oh, yeah.
Not chiral. Achiral. Mirror image is the same thing. Yes, it's tetrahedral. Draw heavy water. But here we go. What if we throw some peroxides in there?
there at the top.
Got that right.
Get that there.
That's an enantiomer.
Classify these reactions as addition or substitution. That's addition,
Addition.
that's addition, that's addition. This is substitution. Maybe that's a consistency. Is Br2 HNu always a substitution? I think it is. HBr is always an addition. And if you do an addition chemistry, it has to be a pi bond, because you can't add to an alkane. And Br2, the old classical Br2, is also an addition. Maybe there's a consistency that you can, instead of the HNu or sort of, Br2H, radical with bromine is always a substitution. Okay, so there's your bromination chemistry. You just can't confuse the chemistry. What's the stereochemistry here? Is it chiral?
Yes.
Yeah, it's chiral. There's no plane of symmetry. I mean, how many stereoisomers possible?
4,
2, 4. So 2 spaces squared.
4 nice.
Yeah, could you draw all four? I think you could. RR, SS, RS, and SR. Which one are you going to get? It's actually going to be all of them. Cation chemistry is racemic. Radical reactions also racemic. You can attack cation either side. You can capture radical either side. The only time you get like inversion is when you do SN2. You get, okay? Or some other type of stereo-specific addition. Bromine adds anti, so it has to be this, plus an enantiomer. I mean, there's 4 stereoisomers possible for this. This reaction only gives 2. And both of these, the bromines are trans. You will not get a product from this reaction where the bromines are cis. You don't get those two. You don't get those two in nature. It can't be meso because there's a methyl. If the methyl wasn't there, then you could possibly have meso where the trans is chiral, but the cis would be not chiral, it would be meso. Since the methyl's there, there's no chance of meso. A lot of review, yeah? Hopefully it's all kind of forming some good connections in the old neuron map.
I thought we couldn't get cis, so then you would never have a meso compound.
You're right, because it's a ring, you're not ever going to get cis. If it was acyclic and it could rotate, you might get cis. We wouldn't call it cis, we'd call it erythro. Because when things can rotate, we need another naming system. Okay, so some review there. Did I finish up the handout? I think so. So that handout material will be on the final exam. Okay. That's the only new stuff. Okay, final exam, just like regular tests, you have some nomenclature. Okay, we had nomenclature on each exam. Some multiple choice, predict the products, maybe product, maybe give reagent, or maybe give starting material. Mechanisms. Be short answers, stereochemistry, like quizzes or test 2, drawing Fisher projections, drawing Newman projections, etc. Basically, everything you were prepared to do on test 1, 2, and 3, you need to be prepared to do on the final exam. Spectroscopy, IR, may be very similar to test 1. Mass spec, may be very similar to test 3. Or it could be sort of a mix. There's a couple of those problems in the workbook. Alkane reactions, I would certainly review. Those are sort of well-defined, specific. Substitution elimination is a little bit more general. Okay, you got to learn all the details and be able to work with it more. Please learn from your mistakes on the test. Other questions? The length is usually my tests are like 4 to 5 pages. Our exam is going to be, I think it's 7, maybe 8 pages. Okay. So it's not double the test. It's like 1 and 2/3 of the test or so. 1 3/4. Not quite double the test. Hopefully you'll find it sort of even more straightforward than test, because lots of this will be just a rehash of the course. Questions? I'll be here tomorrow at 9. If you'd like to do any reviewing. We'll go probably at least an hour and a half, maybe longer, but I will say at least an hour and a half. Question?